Okay, so in the last class, we had completed the feature extraction part. So after feature extraction, the next step is feature selection, right? So that is what we are going to discuss in today's class. Now, I have told you about feature selection in the first class that this particular step is not a compulsory step, but if required, you have to perform it. So under which conditions will you go for feature selection? Say for instance, your feature size is extremely large and you have very limited amount of space in your computer or device, storage device. So at that time, you cannot use all the features for your classification or clustering tasks. So you have to select the best features out of the given set of features. Or say you have to transfer a large collection of features to another device via any channel that has limited bandwidth. So again, you cannot use that large dimension of features. You have to reduce that to the best possible features. So under these type of scenarios, you have to go for feature selection. But if these scenarios are not a constraint in your application, then you might omit this step. Okay. So the most popular type of feature selection method, what we are going to discuss in today's class, is the principal component analysis, that is PCA. So what happens in principal component analysis is that it is basically a dimensionality reduction technique. Okay, so suppose you have a two-dimensional data and you can convert that into a one-dimensional data, something of that sort. Okay, so what is the main motivation behind this type of technique? So over here, what you're going to do is you just have a set of data, or rather the data is nothing but your features which you have extracted via time domain features, frequency domain features, or brain connectivity features, anything. So you have these set of features and you are going to transform that into a different domain to select the most optimal or best features. Okay, that is what we're going to do over here. So let us see one by one the different steps utilized in PCA. So step number 1, vector normalization. Suppose you have, so let there be B number of features, each of size 1 cross n. This is what you already have, right? So the ith input vector can be denoted as xi, xi1, xi2, xin. So this is basically each of your features is of size 1 cross n. That is only your xi. Now you need to normalize each of this feature element. So every element of the vector is normalized as, you know this particular type of normalization technique. Basically, you just take each element and you just divide by the sum of the elements. Okay, so each of your feature element in a vector gets normalized. So vector normalization is over. Next, you have to go for mean free data computation. So for mean free data computation, we have studied that even earlier also, that we simply need to subtract the mean of each of the set of vectors from the individual elements. So basically, if this is your individual element, you subtract the mean value. This is what you have to do for all I and k, and where xi bar is the mean value of the ith vector. So now your data is completely mean free or average free. Okay, so this is the second step. Now let us move on to the third step. Data adjusted matrix. So that means in the first step, we were normalizing each element, and in the second step, we were making it mean free, which is subtracting the mean from it. So whatever equations I've showed you right now is for a single vector, 1 cross n. But how many total such vectors are present? B number of vectors are present. So we can arrange this B number of 1 cross n vectors in a matrix. So that is what we are going to do right now. So this is referred to as the data adjusted matrix. I am saying adjusted because it is normalized and mean free. Okay. So if you put that into a matrix, it looks something like this. So starting from x11, x12 to x1n. So you have b number of features. So it will end at xbn. And the matrix size is going to be b cross n. Right? So this is your final data adjusted matrix. Now upon this matrix, you are going to apply your PCA, that is your principal component analysis, so that you can eliminate the most irrelevant or redundant features and retain the most important information. So the next step is covariance matrix computation. So we have studied earlier how to compute a covariance matrix. You just have to multiply the original matrix with its transpose, right? So if D, we remember, it is B cross N. So D transpose will be N cross B. So the H matrix will be nothing but B cross B. So how does it look? The elements of the H matrix, say H11 to H1b and HB1 to HBB, and it will be a B cross B matrix. So the computation of the covariance matrix is over. Now we move on to the fifth step, that is eigenvalue and eigenvector computation. So you have to compute the eigenvalues and eigenvectors of the H matrix. So all of you know how to calculate eigenvalues and eigenvectors. We have been practicing that for the last couple of classes also. So basically from here you're going to get the eigenvalues, and of course you know how to calculate the eigenvectors. So from this equation you will get the eigenvectors. Okay. Now what we have to estimate is the principal components. So the principal component is nothing but the eigenvector corresponding to the highest eigenvalue. So after performing step number 5, you're going to get a large number of eigenvectors and eigenvalues. But if you have to calculate the principal components, the first thing what you have to retain is the eigenvector corresponding to the highest eigenvalue. So that means you will get one particular vector which has these sort of elements. So this is for lambda largest greater than lambda I, where of course I lies between 1 to b, because we have b number of features. So you're retaining the largest eigenvector, the eigenvector corresponding to the largest eigenvalue. Once you get that, finally, the final step is to project your along the eigenvector corresponding to the largest eigenvalue, E. So we can write Z equal to E transpose cross D. So your E transpose becomes 1 cross B. Your D matrix was B cross N. So ultimately your Z matrix becomes 1 cross N, right? So look at the beauty of this method. Originally you had B cross N number of features. Now you have selected the most optimal or the best feature which has a reduced dimension of 1 cross N. So the dimension was B. Now the dimension is only 1. It's a single dimensional vector, and previously it was a b-dimensional vector. That can be 2-dimensional, 3-dimensional, and so on. So this is how you can reduce the dimension of your features just to retain the most optimal. Optimal feature means the best feature. Okay. Now, geometrically, what does this signify? Let us understand it. So initially, suppose I'm considering a 2-dimensional feature, suppose x1 and x2, okay, and you have certain data points pertaining to this 2-dimensional. So these are the features you have extracted. So this is your data domain. Now, what you are actually doing, you are transforming it to a different domain, say y domain, y1 and y2, and the data is getting projected in some direction in this second y domain. Now you are just retaining the eigenvector corresponding to the largest eigenvalue. That means the projection along which the variance is maximum. Suppose, for instance, the maximum variance is along this projection. So you can keep the data points along this projection and you can remove this particular dimension. So the dimension is reduced and you are just getting the most important features. Okay. So this is the geometrical interpretation of your principal component analysis. Now, the feature selection part is over. We move on to the last part, that is the classifiers. Now we move on to the final stage, that is classification. So it can be classification or clustering, but first we'll discuss classification. So if you remember the basic concept of classification from the first class, under classification we have 2 phases. One is the training phase, where the algorithm learns the labels of the classes, like this data point belongs to C1 class, this data point belongs to C2 class, this data point belongs to C3 class. So all these labels are there and the algorithm simply learns those labels, right? And finally, we have the test phase, where we are just going to provide an unknown data point and we are going to just see whether the algorithm has learned all the labels correctly or not. So by providing an unknown data point, suppose we know that it belongs to class C1, so we're going to check that the algorithm is able to recognize that correctly or not. So we are going to make sure that the learning process of the classifier has been made properly or not. So this is the concept of classification that we had discussed in the first class. Now there are different types of classifiers which can be utilized to perform this task. So one by one, let us see the most important ones. Now whenever I'm talking about classification, suppose I have two classes. Suppose these are the data points that denotes the classes cats, and we have some data points like this which denotes these are for cats and these are for dogs. So my classification task is to categorize the data between cats and dogs. Okay. So automatically the distribution of data, if I'm drawing that into Gaussian distribution, it is something like this. So this is for the cats one and this is for the dog one. Now if the distribution of cats and dog is like this, I cannot discriminate my classes properly. So it's a poor discrimination. So this is not my objective. If my data distribution is something like this, there's a minimum overlap between the technique I'm using. So this is something, it is a good discriminator, right? So this is something which I want to achieve. This is my goal. I have to separate out the data points much more distinctly, right? So that is what we are going to do today. And the first classifier which we are going to use is LDA, that is linear discriminant analysis. Now this LDA classifier has certain concepts very similar to principal component analysis, but there are other modifications also. So in PCA, as we studied a few minutes back, what we are doing is that we are considering the best projection direction of your data points, right? But so this was present. What was not present is that we did not have any class information, because PCA has nothing to do with classification. It is basically a feature selection process. So we had the concept of best projection direction, but there's nothing to do with the class information. So we are just going to extend this concept. So in LDA, we are going to have the concept of best projection as well as we are going to have the class information, so that two classes or more than two classes can be easily discriminated, right? Now, the question is, in LDA, what kind of class information should we have? Best projection we understand from PCA, fine. But class information, what sort of class information should I have so that two classes can be discriminated very easily? So under class information, we can have two types of criteria. So criteria number one, what is my main goal is, we need to maximize the distance between two classes. That is what we are supposed to do. And the second criteria is, we need to minimize the variations within each class. So if we are able to achieve this too, we can easily discriminate two classes. So let me give you an intuitive idea about what kind of distance am I talking about. So suppose I have class 1 and class 2. So these are the data points that belongs to class 1, and these are the data points, suppose they belong to class 2. For class 1, suppose this is the centroid of the data point, or rather the mean value of the class 1, and suppose this is the centroid of class 2. So what is my objective is that I have to maximize the distance between the centroid of class 1 and class 2. So more is the distance between these two centroids, the greater is the separation between the two classes, and higher is the accuracy of my algorithm to recognize the two classes separately, right? So my between class distance, that is the distance between centroids of two classes, that has to be maximized. Okay. Now there is another criteria, that is, I have to minimize the variations within each class. So what do I mean by that? Again, suppose I have class 1 and class 2. So this is what is describing scenario A, and this is what I am describing scenario number B. So we have these data points, and suppose this is the centroid. These are the data points, and suppose this is the centroid. So over here, the distance of the individual data points of a particular class from the centroid. So this accumulated distance I have to minimize. Again, these individual distances from the centroid, the sum of all these distances I have to minimize. So the accumulated distance of, or rather from, the centroid of a class, this has to be minimized. So if they are minimized, that means they are forming small clusters and they are compact within themselves. And if I am increasing the inter-class distances, that is the distance between these two classes, then they are very much separate. So these are the two criteria that I need to keep in mind. So now mathematically, how will I achieve this? Let us understand that. So suppose I have C classes. Each class has Ni m-dimensional samples, where I belongs to 1 to C, because we have total C number of classes, right? So what we are going to do is, we are going to project X, that is the samples we have, to a different domain Y, like we have done in case of PCA. So that is the first task. That means Y is equal to say some matrix W transpose into X. So W is your weight matrix or your projection matrix, and X is your input features, right? So first is we have to project this, but only projection is not the objective. Over here, we have to maintain these two criteria, A and B. That is, we have to maximize between class distance and we have to minimize the variations within each class. So A and B, these two criteria should also be fulfilled. So graphically, what I'm trying to say is, so after performing this particular task, what we'll be able to see is, suppose this is the projection direction. So we have one class of data points, they might have some values, and this will have some other class of data points, they can have certain values. So they are projected along the direction of maximum variance like we have done in PCA, and also they are separated away from each other and they're clearly distinguishable. So all these two things we have to perform parallel, right? So the objective is over here. From here, what is my objective? So the objective is to find the optimum direction of your W matrix. That means you have to find so that it is projected along the maximum variance as well as the inter-class separation is larger and the inter-class separation is smaller, right? Okay. So what are the steps? First, you have to calculate the mean of each class. Mean of each data points in X. So you know that for the input data points, suppose X belongs to a class omega I. This is X, right? Mean of data points after projection suppose it belongs to some class omega I, same thing. So you can break this down mathematically as, you know, Y is equal to W transpose into X, right? So finally you can take out W transpose. So just a minute. So this will be X and you know this is nothing but your, this part is nothing but your mu of I. From here you can get this. So W transpose into mu of I, right? So this is mu I tilde, that is after projection, that is the mean values. Okay. Now you have to calculate within class variance. So it is Si tilde So this is the generalized form. So if I'm just considering two classes, we will simply have S1 tilde square plus S2 tilde square, which is the variability of two classes after projection. Okay. Now, if I am considering the across class means, because that has to be maximized, so this will be evaluated as for two classes mu1 tilde minus mu2 tilde. Very simple. So I can create an objective function j of w as mu1 tilde minus mu2 tilde square divided by s1 tilde square plus s2 tilde square, right? So that means this function has to be maximized. This function needs to be maximized. That means the distance between the mean values have to be large and the within class variations has to be as small as possible. So overall, the function needs to be maximized. But what value will I choose so that this function is maximized? Basically, we need to find out the optimal or the best value of w. But in this equation, the function j of w, we do not have w on the right hand side. Actually, w is hidden between mu and s values. So we have to derive that. This is not complete yet. Okay, so let's continue the process. Now Si, so your covariance matrix before projection can be calculated as Si summation of omega I. You know what is covariance matrix. You just take the matrix and you take its transpose, multiply it that. Okay. You keep this as equation number 2. And there's some, okay. And there was, I think I forgot to mark equation number 1. Just a minute. So this is going to be your equation number 1. Okay, that is your mean value. So from here, we continue the derivation. So if you remember, after projection, so Si tilde was y minus, this was the equation. Now substitute the value of y and mu I tilde. So W transpose X minus W transpose mu of I whole squared. We get that from equation number 1, right? Now this thing can be written as X belongs to omega I, that is one particular class. W transpose X minus mu I, X minus mu I transpose into W. So how am I writing this equation? I'll just give you this rough work part. I'm writing over here so that you can understand. So what is done over here? basically W transpose X minus W transpose mu I whole square. This was the thing. So what I can do is I can take out W transpose X minus mu I, and this is whole square. I hope this part is clear. Now say this thing I am substituting as K. So it's going to be K square. Now over here, this W transpose is a vector and X minus mu I is also a vector. So suppose W transpose is a vector like 1 cross n and X minus mu I will be n cross 1. So automatically this produces a 1 cross 1 scalar. So that means K is a scalar. Okay. Now the scalar quantity K, that means K squared, I can write it as K into K transpose. So it's 2 square. So 2 into transpose of 2 is 2. So it gives me 4. I can write in that manner, right? So in a similar thing, just replace the values. So K into K transpose, so omega T X minus mu I cross omega T transpose of transpose X minus mu I transpose. So transpose of transpose is W, right? So from here, so this is the part what I have written. Okay. So it's just a rough work. I have shown it with a different color. So I'm just drawing these lines in case somebody does not understand this step jump. So I'm just vividly discussing it. Okay. So finally, what we get is I can take out W transpose outside omega I X minus mu I X minus mu I transpose and W outside. And you know this from equation number 2, W transpose into SI into W. This middle part is SI. So this was equation number 2. I'm simply replacing it by SI. Okay. So this is from 2. So in the original equation, that is the equation with J, what we need to find out S1 tilde square and S2 tilde square if you are considering 2 classes. So from this generalized equation, what I get is W transpose S1W plus W transpose S2W. So if I take W transpose and W common, so S1 plus S2 into W. So I can write W transpose S1 plus S2, I can write as SW. Okay. And this can be written as SW tilde. So this SW tilde is nothing but the within class matrix after projection. So it's a within class matrix values. That's why I'm labeling it as S1 plus S2 as SW. Okay. Now similarly, we had another term that is mu1 minus mu2 whole square. So for mu1 tilde minus mu2 tilde, so this is W transpose mu1 minus W transpose mu2. You get this from equation number 1, right? So again, I am taking W transpose mu1 minus mu2, mu1 minus mu2 transpose of W. I can just break it down in this particular fashion as I have shown you a few minutes back. And mu1 minus mu2 and mu2 minus mu2 transpose, I can write as SB of W, and this can be written as SB tilde. So this is the between class matrix values after projection. So this is actually before projection and this is after projection. So anything without tilde is before projection, as we have seen, and anything with tilde is after projection. So basically now JW becomes, we just replace this well, W transpose SB of W divided by W transpose SW of W. So which can be written as SB tilde or SW tilde. So this function needs to be maximized in such a way that an optimal value of W is found. So once we find out the best or optimal value of W, it can be projected along the best possible direction with larger separation between the mean values of the classes and smaller separation within the variance of each class. So this is the function that needs to be optimized. Now, the optimization problem I'm showing you right now is a much more sophisticated optimization problem. So I'm not solving it. Basically, I'm just giving you a brief idea. You must have solved optimization problems at a basic level in your mathematics. Like what you do is you just take the derivative, equate it to 0, you find out the minimum and maximum values, and then you check with those values whether the function is maximized or minimized, right? So same thing is also done over here. But ultimately, it's a much more sophisticated optimization problem because we try to obtain the value using a generalized eigenvalue problem. So I'm not getting into those high level of mathematics, but this is the basic principle of linear discriminant analysis. I hope this part is clear. Any doubts still here? Okay. So this is the first classifier, what we have discussed today. Now we move on to the second classifier, that is called as support vector machine, SVM. All right. Now, support vector machine is a much more simpler concept as compared to the previous classifier, that is LDA. What happens over here is that suppose I am considering a two-dimensional feature. So plus belongs to one particular class and the round ones are something else. Now, if I have to separate these two classes, so instead of projection, what I can do is I can simply draw a straight line that is going to separate these two classes, right? So this particular line is referred to as a decision boundary. So I can simply draw a decision boundary and separate the two classes. So I don't have to go for projection and calculation of all those distances. Those things are not required. It is much more simplified, right? Now, since I am considering a two-dimensional system, so I'm having 2D features, so this decision boundary, if I am in two-dimensional system, the decision boundary is a line as I have drawn right now. If it's a three-dimensional feature space, the line becomes what? Any idea? If it's in three-dimensional, it is no longer a line, the decision boundary, it becomes something else. Any idea? It basically becomes a plane. And if it is higher dimensional, then it becomes a hyperplane. Okay. So, but the main objective over here is to calculate this decision boundary. So again, we are going to utilize a particular function to mathematically evaluate the decision boundary. So the decision boundary, say g of x, is W transpose of x plus b. This is the basic equation of a decision boundary. So this particular equation is very similar to the equation of a straight line. if you can compare mx plus c, right? Y is equal to mx plus c, something of that sort. Now this Wt is of course your weight matrix, but this denotes the orientation of the plane or hyperplane or line, depending on the dimension you are in. X, you know, you have your input features, and B is deciding the position of the plane. And this has a particular technical term, it is called the bias term. Okay, so the W transpose is deciding the orientation of your plane or line, and B is denoting the position of your plane or line. Now the philosophy we understand, it is a very simpler philosophy. We are simply drawing a line if it's in 2 dimension. However, there is one particular confusion. What is that confusion? Again, let me draw the data points. So this is your decision boundary, basically a line. Now, how will I draw this decision boundary? So in this scenario, I can draw this line in this particular way. I can make the line something like this. I can make the line something like this. So I can have first decision boundary, second decision boundary, third decision boundary. And if I keep on drawing, I can have infinite number of decision boundaries, right? Somebody can use decision boundary number 2, somebody will use decision boundary number 3, and so on and so forth. So the question over here is that, how can I find out the best decision boundary? How do I find it out? Of course, that will be dependent on minimum error rate in classification. That means the classifier will be able to produce 100% accuracy or near 100% accuracy. So I have to choose such kind of a decision boundary, right? That will give me cent% accuracy as far as possible. How to do that? That is the question. So the solution to this so I'm drawing the feature space again. So I can utilize a single line to separate these two set of points, but instead of that, what I'm going to do is I am going to draw a line having some thickness, right? This thickness is the margin. So over here, I'm interested in the width of the decision boundary just before hitting the point. So I have to draw this decision boundary in such a way that the points belonging to each of the classes, they just lie on the boundary of the particular decision boundary. This is my objective. So right now, my goal is to find out the optimal value of this margin. How much margin or how much width of the decision boundary should be there such that the separation can be done in this particular fashion, that some of the points will lie on one side of the boundary and the other points of belonging to the other class will lie on the other side of the boundary. This is the most optimal way in which I can classify the two classes, right? So what I can do over here is, in this diagram, suppose originally the decision boundary, that can be written as W transpose X plus B equal to 0. That was a straight line. So if I'm saying the ones on the upper side, they have a class label of +1, and the ones on the lower side, they have a class label of -1, then this particular equation can be written as W transpose, suppose this is xi plus B is greater than 0. So if the middle line is equal to 0, something lying above it is greater than 0. And this particular decision boundary, W transpose xi plus B, is less than 0. This is how I can mathematically define these two classes, right? So let me just write down what I have written in the diagram. So what I'm trying to do is, for a given set of data points xi, we can assign its belongness as yi. That means this +1 and -1, these are the class labels I'm assigning. So what I'm trying to say is, for yi equal to +1, W transpose xi plus B is greater than 0. That means you have the points on upper side of the decision boundary, right? And for yi equal to -1, W transpose xi plus B is less than 0. That means points on the lower side. Now in this equation, suppose we perform some scaling. So this W new is equal to W old by some value gamma, and B new equal to B old by some value gamma. Okay. Now how am I choosing gamma? Gamma is chosen such that the margin of the closest points is equal to 1. I'm explaining what I'm trying to say. So basically, the equation what we wrote for yi equal to +1, W transpose xi plus B now becomes greater than equal to 1, and yi equal to -1, W transpose xi plus B now becomes less than equal to less than 1. So in the first equation, what is the interpretation? Previously, if yi equal to +1, this equation was explaining that the data points were on the upper side of the decision boundary. Now it is saying that the points are on the upper side of the decision boundary. Yes, that condition is still there, but at least there is an extra point with this, that at least these data points are 1 unit away from the boundary. That means the points are on the upper side and at least 1 unit away from the decision boundary. That means if I'm coming back to the diagram, so I'm performing small amount of scaling. Which color will I use? Suppose, no, green, yeah. So that means this particular distance from the decision boundary should be at least 1 unit. That is how I am reorganizing or scaling these two equations, this one and this one. Okay, this is just a scaling, it just means the same thing. Okay. So we found out the equations for two different types of classes, but ultimate objective is what? We have to find out the margin width, the optimal margin width. This is my objective. I have to find it out, right? So how do I do that? So let's go for the calculation of margin width. Now just a brief brush up. So I'm writing as a note. For two parallel lines, if you remember from mathematics, ax plus by plus c1 if it's 0 and ax plus by plus c2 if it is 0, the distance between the two lines is c2 minus c1 by modulus of a square plus b square, right? So similar to this, for two hyperplanes, if I'm considering, w1 x1 plus w2 x2 plus b minus 1 equal to 0, w1 x1 w2 x2 plus b plus 1 equal to 0. Suppose these are the two hyperplanes. So the distance d will be evaluated as this w1 squared w2 squared. Finally, we get 2 divided by modulus of w. So now, so this is your margin. So the objective over here is I have to maximize this value such that under two conditions, that is yi is plus 1, w transpose xi plus b1 is greater than equal to 1, and yi equal to minus 1 when w transpose xi plus bi is less than 1. So again, minus 1. So under these two conditions, I have to maximize this particular quantity, keeping these conditions intact. And generally what we use is a Lagrange's multiplier. I do not know whether you're familiar with the technique or not, so I'm not going to discuss that in details. So this is the basic philosophy of support vector machine. One thing we need to discuss is that I'm saying it's support vector machine. So there is a term called support vectors, right? So from this term support vectors, the algorithm has been labeled as support vector machines. So what are support vectors? So in the diagram we had drawn, so these vectors which are sitting on the boundary of the hyperplane, these are only the support vectors. And the support vectors are the only vectors through which I can calculate my optimal margin, right? So support vectors are nothing but, I'm writing over here, just a minute, I think there's some problem with the board. Give me a minute. Okay, so we were seeing about support vectors. So support vectors are the points which lie on the boundaries of the hyperplane that helps me to decide the margin of the hyperplane, and hence the name support vector machine. Okay. Is it clear to everyone what are support vector machines and what is LDA? Any doubts still here?
No, ma'am.
Okay. So now we move on to another category of classifiers, that is a multi-layer perceptron. Now, what is a multi-layer perceptron? Before that, so basically a perceptron or a multi-layer perceptron, it is nothing but your artificial neural network. That is what we're going to study. And we're going to see how to utilize an artificial neural network for the classification task. Now, if you remember the structure of a biological neuron, just for revision, I'm going to draw it again. So you had the cell body, these are your dendrites, and this is your axon, right? So you have your dendrites, this is your cell body, this is your axon, and if there is a link between the axon of another neuron and this neuron, so a synapse will be created. Or there can be different other types of synapses. That is what we have discussed. So there are basically 4 components with which we are going to build an artificial neuron. So let us see how does an artificial neuron look like. So an artificial neuron looks something like this. You have some inputs x1, x2, x3, okay. Corresponding to the inputs, you have some weights. You can have a bias term B over here. So this is basically a summer. So it will basically multiply the weights with your inputs and sum those values, and finally you will add a bias term. So whatever is the output, that is your net value, and the net value is sent to a non-linear unit. And then you're going to have some out value. So over here, if I'm using a different color, okay. So first of all, your inputs, that means x1 and x2, these are your inputs. So they are acting as your dendrites. So dendrites are collecting the information from your muscles and other parts of the body, right? Okay. Now the summer is acting as the cell body, okay? And the non-linear unit is your synapse, and this net value is nothing but your axle. Okay. So mathematically, I can write down your net value as summation of I equal to 1 to some n omega I xi plus bi, which is your bias term. Now I'm saying we have some out value and we have a nonlinear unit. What is the function of this nonlinear unit? So from net you're going to get some value 1, 2, 3, 4, some value, right? So nonlinear unit, the main function is to limit the value of net within a range. So range can be between 0 and 1, between -1, +1, and so on. So how do I do that? So basically, for instance, your out value can be a sigmoid function. I mean, the net value can be applied to a sigmoid function to get the out value. All of you know what a sigmoid function is. This is a sigmoid function. So your out value gets limited between 0 to 1. Or your out value can be designed as a hyperbolic tangent function. So your value gets limited between +1 to -1. So you can use different types of functions in order to limit the value of your out. Okay. Now these are all nonlinear functions, sigmoid function, hyperbolic tangent. You are familiar with all those functions, right? So these nonlinear functions, where I'm applying it to any kind of artificial neural network, they are referred to as activation functions. Okay, so this is the term which is used. Activation functions, so nonlinear functions. And you can use any type of function as per your need. Now, so this is the structure of an artificial neuron, or it is referred to as a perceptron. Okay. Now, as an example, I'm going to show you how can I use a perceptron to categorize between two class tables. So as an example, what I can do is, I have this summer. Suppose I have two inputs, x1, x2, okay. Suppose the weights are -2 and the bias is suppose +3. So I have a summer, I have a nonlinear unit, and I get some output A is equal to f of z. So what am I signifying this as? So from here what we get is z equal to -2x1 minus 2x2 plus 3. Okay. So f of z, that is the final output, that has two ranges. It belongs to class 0 if the value of z is less than equal to 0, or it belongs to class 1 if the value of z is greater than 0. So diagrammatically, what I'm trying to say is, if I have a two-dimensional feature space, this is the line which I am deciding. Suppose this is of 1 unit, -2x1 minus 2x2 plus 3. We can understand it's going to be a straight line like this, right? So if your data point lies in this particular region, that is z is less than equal to 0, that means a equal to 0. So this, the right hand side of this line, so it belongs to one particular class. And if it lies over here, that is a equal to 1, when z value is greater than 0, this is another region. So this belongs to another class. So this is how I am separating the space into two different regions. Two different regions means two different classes. So this is how I can use a perceptron to classify between two classes. Now, a perceptron can be, this diagram which I have drawn, we have a summer and a nonlinear unit. But the short form of a perceptron we do not draw it generally with one summer and nonlinear unit. We draw one particular circle. So this is one perceptron for simplicity. Okay. So within this perceptron, we have a summer as well as some function which is a nonlinear function. So if this is my input and we'll have some output. Okay. So this is the short form of drawing a perceptron. Now the question is, the diagram I showed right now, this is a very simple diagram. So with the one straight line, you can easily separate out two data points. But if the data points are scattered in such a way that one single line cannot separate them easily, then how to do it? So suppose I'm saying I have this data points x1 and x2, okay, and suppose these are the data points belonging to one class. And the circle ones are data points belonging to some other class. So for that, what can be done is, we can draw this one line, one decision boundary that can separate this part. We can draw this line. We have to draw another line like this. So suppose this is number 2, this is number 3, and finally we can draw this like this. This is number 4. So by drawing 4 number of lines, we can finally separate out two different classes. But this separation is very complicated. But we are going to design this complexity using a perceptron, but not via single perceptron, because a single perceptron can only separate out these two regions, as we have seen earlier. For making a complex separation like the one I am showing over here, we have to use multiple number of perceptrons. So for that, what we can have? These are your input points x1 and x2. So I have drawn 4 different lines. So I need 4 different perceptrons, each perceptron for one line, right? So 1, 2, 3, 4. And now, as usual, we are going to have a connection. We are going to have some weight values corresponding to the connections of each perceptron. And all these perceptrons are going to meet at a single point and give you some out value. If out is 0 or out value can be 1, depending on it belongs to class number, say C1, or it belongs to class number C2. So since we are using a large number of perceptrons, this is actually a multi-layer perceptron. Okay, so let me draw this diagram officially, like what a multi-layer perceptron looks like. Multi-layer perceptron. In fact, a multi-layer perceptron, it is able to handle complexity between two classes, like we have seen. It can also handle easily a multi-class classification problem. So I do not consider a single class, I can have 10 classes, 20 classes with all these complexities. So for that, what we have? Usually, we have an input layer. So input layer is always we draw it with squares, okay? In all the books, you will see the input layer is also a circle. So perceptron is also a circle, input layer is also a circle. That is very confusing. So that is not the correct method, okay? The input layer, we can use square, triangle, anything else, not a circle. So you are going to have certain perceptrons. And suppose it's a 3-class classification problem. So we're going to have 3 perceptrons at the output. So each of them are going to have connections which each of the perceptron so like this, and each of these perceptrons will again have connections like this. Okay. So this layer is referred to as the input layer. This layer is referred to as the hidden layer. So it can be one hidden layer, it can be multiple number of hidden layers, depending on your application. And the last one is an output layer. So 1, 2, 3, 4 perceptrons here, say 1 dash, 2 dash, 3 dash. 3 perceptrons at the output. So in the output, whatever is the total number of classes, so many number of perceptron has to be there. So if I have to decide that an input vector which I have provided, that belongs to say class number 2. So how will I understand? By looking at the output. So these values will be 0 and this value will be 1. If this is 1, that means it belongs to class number 2. If the value of 1 dash is 1, that means it belongs to class number 1. The other values will be 0. That is how we can understand. Now over here, we have to assign weights. So how do we write the weights? So the one link that is connecting from x1 to perceptron number 1, we say W11, this one would be W12 and so on and so forth. Again from hidden layer to output layer, we say G11 dash, G12 dash and so on. This is how we label the weights. So the classification is fine. Of course, we have to go for an optimization of the weights such that the accuracy of your classifier is maximized. Now, there is a very famous algorithm which is referred to as the backpropagation algorithm. So there is a huge derivation on the backpropagation of algorithm that helps me to decide the optimal values of those weights so that the classification problem or the accuracy of the classifier is maximized. Okay. So we are not getting into the optimization case. So this is the basic principle of multi-layer perceptron that I wanted to discuss. So any doubts still here?
No, ma'am.
Okay. So let us end over here. We are left with another classifier. I think it's better to continue in the next class. So the next class will be the last class where I'll complete the syllabus, and after a day I'll provide you the assignment which you need to solve within 5 days. Okay. When is your exam starting? First week of May? 6th or 7th of May. Okay, fine. Do not worry, before your written exam also, I will also provide a suggestion. Do study the suggestion very carefully. Hopefully at least 80 to 90% of the questions will come from the suggestions. Okay, fine. Yes. Previous year questions I can provide, but the thing is till last, I think last year this open elective was not taken by the ETC department as long as I remember. Before that Professor Konar used to take the class, and at that time the syllabus was completely different. I mean there was some commonality, but there was a lot of difference. So this year it's a new syllabus which I am teaching. Yeah, suggestion I'll definitely give, and do read, I mean study each and every question. Do not leave out any question from the suggestions, because generally 80 to 90% of the questions come from there. Okay. All right. So I'm ending the class. Thank you all of you.